the electric field. That's what we're going to do now. Okay, these are just two rubber balls. But suppose that these are electrically charged objects. It turns out that there is a electric interaction between these two that depends on really two main things. It depends on the values of these two charges, and it depends on the distance between them. And we call this Coulomb's law. And it's just there's no way to derive this. It's just a fundamental law of nature. Okay, we can experimentally show that there is, as you get these closer together, the force between them gets greater. It could be either repulsive, push them apart, or attractive, depending on the charges. If they're the same charge, they repel. If they're the opposite charges, they attract. So that's Coulomb's law. And one thing that we can do is, with Coulomb's law, which I'm going to write down in a second, is to calculate the force on this charge due to this one, and then divide by the magnitude of this charge, and you get the force per unit charge right here. And that's the electric field. And there's an electric field surrounding this charge, and it actually turns out to be super useful. So we're going to calculate the electric field due to one charge, and then we're going to calculate the electric field due to two charges at some other location up here. It's going to be great. Okay, so let's start with the expression for Coulomb's law, okay, because it's useful. So this says that the electric force, the magnitude of electric force, is K Q1 Q2 over R squared. So K is a constant, 9 times 10 to the 9th newtons meters squared per Coulomb squared, and Coulomb is a unit of charge. So this gives us the magnitude of the force between those things. But it's not super useful because everything's written as a scalar value. And so once we get to more complicated problems, this is just worthless. Okay, this constant's important, and I'll put it up here. K equals 9 times 10 to the 9th times Newton meters squared per Coulomb squared. Okay, so if I want to calculate the electric field, I have a couple of options. I have a couple ways I can write that. I can write this as E equals K Q over the magnitude of R squared times R hat. Remember, that's that unit vector that we had before. And I'm going to draw you a picture in just a second. You could write it also like this. K Q R over the magnitude of R cubed. Because remember, R divided by the magnitude of R is R hat. So these two things are the same way. I'm going to use this formula, but if you don't want to do unit vectors, you could do the second one. Okay, let's just jump into it and let's just calculate the electric field and see what happens. Okay, so let's suppose I have a charge right there at the origin, and I want to find the electric field right there. Okay, so I'm going to write down a couple things. The location of my charge, Q, is going to be the vector 0, 0, 0. The magnitude of the charge, I'm picking something. So let's say it's 5 nanocoulombs. Okay, so that means 5. This has units of coulombs, so I can't use nanocoulombs. So I need to convert this to coulombs. So this, and I should do unit conversion. Okay, I'll do it. Since I made that video, I can't just skip that. Okay, so I know that there are in 1 coulomb, let's say 10 to the negative 9th coulombs is 1 nanocoulomb. So these cancel, and I get Q is 5 times 10 to the negative 9th coulombs. Are we cool with that? Okay. Now I need the location of my observation location. I'll call it RO. And that's going to be, I wrote it down here, 0.100 meters. So it's 10 centimeters away. Okay, so the first thing we need to do, I want to calculate this vector R. And that might seem trivial to you because like, hey, you already gave it to me. You told me where that location is. But that's only true because the charge is at the origin. If the charge was not at the origin, then this wouldn't work. So in fact, in order to find R, I can say R equals RO minus RQ. But RQ is 0, 0, 0, so R is just RO. Okay. So 0.100. Next, I need to find the magnitude of R. I need to find the magnitude of R because it's right down here in this equation. So let's find that. R magnitude. Well, it's going to be the square root of 0.1 squared plus 0 squared plus 0 squared meters. So that's 0.1 meter. That's pretty easy. I picked the easy ones, right? We got to start off easy. Now I want to find R hat. R hat is R divided by the magnitude of R. Again, this one's pretty easy because I have 0.100 meters divided by 0.1 meters, so I get 100, no units. So I have K, I have Q, I have R hat, I have the magnitude of R, which I can square. So we can put in all our things. I'm going to erase this right here and put it in right here. E equals K Q R hat over the magnitude of R squared. So that's going to be 9 times 10 to the 9th. I'll leave off the units. 5 times 10 to the negative 9. 1 0, that's a vector. 1 0 0. That's important because when we get at the end, since I'm multiplying by a vector, I get a vector answer, which the electric field is a vector. Okay. And then I need to divide this by 0.1 squared. And again, there should be units in there, but I'm just trying to save space. And if I do that, if I multiply all this stuff and then multiply it by 100, I get this. 4,500. I already worked it out. Yeah, that's 4,500, 0, newtons per coulomb, and that's units for electric field. So there we did it. That's the electric field due to a point charge. You can move it at different locations and all that stuff. But that's just an intro. Okay, I'll stop here, and I'll make another video using 2 charges.